Okay, this is the control side of Stan. Ryan's told you about the mains input and the sort of heavy duty power control. This is the more delicate control system of Stan. Nearly all the controls are CAN based, control area network based. So there's a CAN bus that goes pretty much all the way around the machine. Nearly all of the optics and the servos for the optics are CAN controlled. The main power supplies are CAN controlled. The water system is CAN controlled, so it's a bit like a car in that sense. And on the panel here, the CAN bus is distributed. There's a microprocessor controller in here. The system has been used for CNC operation, so it has pre-programmed functions built into it. There is also on here an RS422 port to allow computer control, so you can actually fine-tune all of the parameters of the system. We don't have the full protocol for that at the moment. We've identified some of the control protocol for it, and we're hoping that we'll get more information as we power it up as to the error codes, etc. Or we can just sit on the CAN bus and monitor that, again, a bit like you would with an ODB on a car. We're simulating a number of the control systems. So here we build a box which simulates the electronic control system for the startup, and there's another similar box which actually then fires the laser and emulates the CNC system. So we've had to do quite a lot of rewiring of this part of it because we don't have the original CNC system that it was used with.
Cool. So down here we have the output end of the 3 power supplies. So you can see 1, 2, 3 supplies. The water cooling for them is here, and the output is here. So they each have two separate outputs. So I think there's 2 sets of diode bars in series for each power supply. So there's actually 6 circuits that get supplied with DC from these. Again, the power supplies are water cooled as well, and yeah, they're massive. They're ridiculously huge, 10,000 watts each. The scale of this thing is on a completely different level to any type of laser that I've worked on before. You'll find a lot of times lasers, the power supply is as important as the optics and the gain medium and all that sort of jazz. With this one, it's the same, but it's just that everything is so much larger and so much more powerful. It's very well engineered. Everything has been thought about. All of the water supplies are measured and metered and flow controlled and interlocked and everything. In the manual, there's 2 pages of schematic for the water supply. It's an incredibly complicated bit of system, and hopefully we can get to grips with it and get it running. So this is the water end of the system. This is the water supply, I guess you would call it. There is a reservoir, a big filter, massive, a deionizing filter, a deionizing cartridge, and a water controller. So this controls all the valves, pumps, everything for the water supply throughout the laser system. There's a fill tube and a sort of overflow thing, temperature sensor inside the reservoir, and behind all of this, which you can't see but fills most of that space, is a pump. The water supply for this laser, the service it requires is 4,700 liters per hour at 5 bar. So 5 bar, to put that in terms of head, that's 50 meters of head. So with the pump that we need to put water into this laser, if we ran it to the specification that it requires in the manual, you'd be able to pump water up 50 meters of pipe. So it's a very serious bit of engineering. It's all HDPE, very well sealed stuff. It's again interlocked and controlled, and valves everywhere, and it's very complex. But hopefully we can get it running. This is the bit of system that's preventing us from just turning it on and running with it. We need to make this guy happy before we can get to the next stage in the initialization or startup procedure. So that's where we are right now.